Good afternoon, and thank you everyone for joining myself and my fellow presenters today. My name is Kelsey Reese, and I am currently a PhD candidate at the University of Notre Dame in the Department of Anthropology. This summer, I was a Future Park Leaders intern at the Valles Caldera National Preserve and produced a geospatial model to assess archaeological site vulnerability to direct wildland fire effects. The Valles Caldera National Preserve is located in north-central New Mexico within the Jemez mountain range produced by 13 million years of volcanic activity. About 1.2 million years ago, a magma chamber that had formed from recent eruptions collapsed into itself and created the 12 to 15 mile wide Valles Caldera that you can see pictured here. The natural resources left behind by this geologic creation story are fundamental to why this area has been continuously occupied by people over the past 12,000 years. Paleo-Indian and archaic peoples made projectile points from local obsidian. Ancestral people, Pueblo people cultivated high-altitude maize farming plots. Old-growth timber logging occurred throughout the 19th and 20th centuries, and we are obviously still using it today. Changing climatic regimes, however, have resulted in more frequent and catastrophic wildland fire events over the past 2 decades. Since the year 2000, 63% of the preserve and 50% of recorded archaeological sites have been exposed to some type of unplanned fire event. The geospatial model I am presenting today takes a 3-part approach to inform future management decisions to mitigate wildland fire effects. The first utilizes past survey to quantify vulnerability of archaeological sites to direct fire effects. The second uses real-time, hyper-localized weather data to identify areas on the preserve most susceptible to a wildland fire event. And the third predicts the total extent of cultural resources on the preserve to guide future research and mitigation efforts. Part 1 of this model systematically quantified archaeological site vulnerability by tallying frequencies of features present in each site, normalizing the frequencies across features, transforming the normalized features with perceived sensitivity and priority for protection rankings, and then past thinning, prescription, and wildfire events were added to produce a standardized vulnerability score. The vulnerability score is calculated for all recorded archaeological sites in the preserve and are plotted on a continuous green to red color scale. While this illustration provides the ability to quickly glance at individual sites and identify vulnerability in relation to one another, we can better assess the most vulnerable districts of sites by applying a kernel density analysis. The figure shows results of a density analysis that uses the previously calculated vulnerability score as weights for each recorded site on the preserve. The result of this analysis makes it much easier to identify clusters or districts of sites that are most vulnerable to direct fire effects. The vulnerability of these archaeological sites, however, do not exist in a sterile landscape without a multitude of other variables. We are fortunate at the preserve to have a host of local weather collection stations, shown here as the blue dots, recording a plethora of information every hour of the day, showing up at the top of the screen. This means we can use real-time weather data to inform immediate threats on cultural resources across the preserve. For example, we can calculate a localized Keach-Virum Drought Index, or KBDI, for each weather station across the preserve. The color scale you're seeing here is for today, August 19th, where the blue end of the spectrum represents no to low moisture depletion, and the red end of the spectrum represents increasingly dry conditions. We can add this real-time assessment to understanding archaeological site vulnerability by multiplying the last weighted kernel density analysis with the one weighted by the KBDI to quickly identify the clusters of sites most vulnerable today at this very moment to wildland fire by condensing the types of features present on each site, the vulnerability of those features to direct fire effects, and the immediate weather conditions that directly affect the archaeological sites themselves. While these models are helpful for informing management and mitigation on a day-to-day basis, we must remember that they only reflect the archaeological sites that have been recorded thus far. Less than half the preserve has been surveyed and therefore leaves the potential for many archaeological sites that are vulnerable to direct fire effects. To help inform future research and mitigation efforts, I've produced a model to predict potential site locations by categories of site use. The model takes into account all of the layers you are seeing on the screen with a few caveats. The range of years for the maize growing niche model are tailored to the corresponding periods of sites being predicted, and the obsidian quarry, pathways, and woodland layers are used for predicting specific site types. The results of the predictive model suggest areas that are most likely to have archaeological sites related to the corresponding category of site use. The results of this predictive model can be used to guide future archaeological survey efforts, but can also be used to prioritize areas for wildland fire mitigation treatments by identifying subregions most likely to contain vulnerable cultural resources. Putting all of these metrics together, we can identify the most pressing area for fire mitigation in the future based on the density of sites by type and the current risk for wildland fire. And before I end, I just want to quickly thank Stephanie Bergman, everyone at the Preserve, the Santa Fe National Forest, Bandelier National Monument, the National Park Service, and of course, the Ecological Society of America for making this all possible.